Hey everyone, we're now moving on to question 11 in the 2019 B test. The question reads, consider a flat uniform square of mass m and side length L. Cut a circle out of the square that has a diameter equal to the length of the side of the square. So we originally have this square right here that has a mass of m and then side length L, and we're cutting this circle out. Hopefully that's good enough circle. So here's the remaining parts of this object that's left after we've cut it out. Okay, so determine the moment of inertia of the remaining shape about an axis through the center and perpendicular to the plane of the square. So basically this axis is coming in and out of the page in this drawing. So if you recall, the formula for the moment of inertia is mr, the summation of all the m times r squared in your object. So you can imagine if you have an object and then you subtract some mass from it, you can imagine you're just subtracting the moment of inertia as well, because this is just a summation of all the masses times r squared, right? So I think actually the easiest way to do this problem is to memorize, if you have already memorized, the moment of inertia of the square and moment of inertia of a circle. These you can find on Wikipedia. Just search up moment of inertia of common objects and you can go through and memorize as many as you can. So this is what the moment of inertia of a square is, and this is what the moment of inertia of a circle is, straight from Wikipedia. You do have to be careful though, because sometimes the Wikipedia will give you moment of inertia like through a different axes than we want. Maybe it gives you a moment of inertia like this, which won't be helpful for us because we want the moment of inertia through the center of the page, so through the page going in and out of the page. So you have to be careful about where the axis is. I'll also go over at the end of this video how to calculate the moment of inertia using calculus, but you'll definitely be free to skip that part because FEOS-MA is not a calculus-based test. So let's start with the intuition that we can just subtract the moment of inertia of the circle from the moment of inertia of the square. So we already have 1/6 ml squared as the moment of inertia of the square. So we want to subtract the moment of inertia of the circle. Now we might be tempted to just plug this directly into here, but we have to be careful. This equation that I pulled from Wikipedia, this is considering the mass m as the entire mass. However, it's kind of apparent that the mass here, alright, sorry about that. So where we were talking about the mass in this equation. So it's apparent that this mass and this mass are not the same, but they're given it as the same variables here. And the reason is because the mass of the circle that you're cutting out is obviously not the entire mass of the rectangle. Otherwise, you're cutting out the entire rectangle, right? So what is this mass of the circle? So I'm gonna call it the mass MC as the mass of the circle. Well, it says that it's a flat uniform square, so that means that the density is constant, right? So if we have m over v, that's going to be constant. So that means also then the mass of the circle divided by the area of the circle, which is pi r squared, so length over 2 squared. This is equal to density, which is also equal to the mass of the rectangle, or the square, divided by length squared, right? So that means that we have that MC is equal to m over L squared times pi L squared over 4. So these guys cancel out. This gives us m over 4. Sorry, maybe I'll just write it as pi over 4 m. Okay, so we can now plug this MC back into this MC, so then now we have the same variable for the mass throughout. So then minus 1/8 times pi over 4 m, and then d stands for the diameter, so diameter is length, so it's still L squared. Okay, if we simplify this a little bit, then that gives us, let's see, so this is pi over 32, so we can multiply, what's the lowest common denominator? well, we don't actually need to find the lowest common denominator, we can just keep it like this. So this is ml squared 1/6 ml squared minus this, so then this is actually one of the answer choices right here. 1/6, so we're just factoring out the ml squared from this term right here. But like I promised, I'm going to also cover how to calculate the moment of inertia of these shapes, of these weird shapes, using calculus. So definitely you can feel free to skip this part of the video, but here it is. So first of all, let's first look at the moment of inertia of a square. So we want to do the summation of all the mr squared in this uniform shape. So we just take the integral of all the m dm r squared. So every small mass element times its radius from the center, okay? Let's start, since this thing is symmetric, obviously on all four sides, I think it's easy to split it off. So maybe if we calculate this, the moment of inertia through this area first, and we can just multiply it by 4 because it's the same for all 4 of these subsections, okay? And this will make our calculations a bit easier, okay? So how we will do this now is look at the every dm. What exactly is the dm? dm is, say, like a small square element right here, okay? It has many of these small square elements, and all of these dm's make up the entire m of the square, okay? So again, we can use the fact that mass over volume is equal to density. You'll be using this a lot, basically anytime where it gives you that it's constant density. So because of this, then we can say dm over whatever the d volume is, or d area in this case is. So what is this d area? Well, we can model it as dx times dy, right? So dx will be a small increment in x, and dy will be a small increment in y, and you multiply it as like a small little rectangle that the dm is in. So this is also equal to the same density, okay? So we can actually plug this, so dm right here is equal to rho dx dy, right? So we can plug that into dm. And the reason we want to have dx dy right here is because we actually can represent we can represent the radius in terms of x and y, right? If we imagine this as our coordinate grid, the radius, how far away it is from the origin, is just x squared plus y squared. The square root of x squared plus y squared, right? So that's r, but we don't actually need to write it as that because we want r squared. So, well, actually, I'll just write r squared is equal to x squared plus y squared, right? That's just from a Pythagorean theorem. So then we can write this as I'm plugging in r squared to here, and then I'm plugging in dm to here. So that will give us rho times, well, actually, I'll just take the rho out of the equation because it's a constant. And then times x squared plus y squared, okay? And then dx dy, and since we have two variables that we're integrating, yes, we're going to take a double integral of this function. And this is actually a lot easier than it might look, because this is a relatively simple function on the inside. So now let's look at the bounds for the integration. Let's first do, it doesn't matter what order you do it in, but let's first do x. Obviously the x goes from 0 to whatever to this place right here, which we're actually, since we're considering this to be half of the distance of L, right? So if this entire distance L, that means this distance right here that we consider is L over 2, and it's the exact same thing for the y. So this is the integral that we're looking for. If we solve this integral, we're gonna get the right answer. Let's solve it right now. So let's first take the dx. So we're basically considering y as constant, and then we're taking the integral of x. So this becomes x cubed over 3. Taking this bound, okay, plus, and then so y is basically a constant. So basically we will just treat it as integrating constant. And this is integrated from 0 to L over 2. And remember, this is applying to the x variable, not the y variable. And we still have to do another integral for the y. So then we get simplifying this some more, it's L cubed over 8 times 3 plus y squared times L over 2, right? Now we're taking this again, L over 2 density dy. So if we integrate it in terms of y, then that means that this is just L cubed 8 times 3 times y, taken from 0 to L over 2, plus, and then this is y cubed over 3, taken from 0 to L over 2 times L over 2. And that gives us, if we plug this in, that's L to the power 4 over 8 times 3 times 2, right? Plus, this is also L to the power 4 divided by, so this is L over 2 cubed, so that's L cubed over 8, and we're having L cubed times L is L to the power 4, so then in the denominator we also have 8 times 3 times 2, okay? And this entire thing is multiplied by the density, and we already know that the density we already defined is mass over volume, right? Oh, by the way, one thing I forgot to do is to multiply by 4, so actually I'll just do that right now. This is actually 4 times it because we calculated the moment of inertia for one of these squares, so that means that if we want to calculate for all 4, we just multiply by 4. Okay, and then now let's plug back in the density, and since we know density is mass over volume, the mass of the entire square divided by the volume, which is actually just L squared, right? So if we plug that into, oops, we plug this into here. First, let me just cancel this guy out. Then you have m over L squared times L to the power 4 over, and this is what, 12 plus L to the power 4 over 12, so squared, so this guy becomes squared, and what we get is now, so we can add these two together, so it's m L squared over 6, and that's what we get, 1/6 ml squared. You can apply the exact same reasoning to find the moment of inertia of the circle. You can use dx and dy, but instead of using L over 2 as the bounds, then you can instead use square root of, because we're considering this circle now, this semicircle as the bounds now, so you could do it by considering that as the bounds, or another thing that might be easier is to use polar coordinates and integrate it. But yeah, it might be easier for you to actually, during the test, to memorize all the moment of inertias, because this thing actually gets a bit time consuming and you might make some mistake.